All right, hi everyone. We are looking at some design questions to do with arrays for Wolfram language. And this is a continuation of some meetings that we had a few months ago, working towards streamlining how one deals with arrays. So where is the whole inserting? Is this here? Is this the insertion story?
Right. I would include it in the second part of this, where I say alternative default rules for thread. But because we don't have Tally today, I wasn't planning to discuss that particular.
But wait a second. But we had already made this design of this insertion thing, right? What happened to that?
We had some ideas. We didn't have a design.
Exactly.
Well, we had a large part of the design. I think that's something we need to finish. And that's something that Etienne is also involved with. Is Etienne here or not?
I tried calling him, but I haven't gotten a hold of him yet.
Okay. So I think we basically should go back to what I had already worked on, written down before. So we have an August 31st one. So this was, okay, so this is this insertion idea, right? And where is the most recent version of the insertion idea?
There's a notebook called Array Reduce, and something
but
else.
The Array Reduce is something that was in 12.2.
Right. And yeah, and then there's an Array Operations 03.
Yeah, I already looked at that. That's what I just pulled up.
Right. So that's something that Etienne wrote, but there is no insertion there.
Where is this?
No, I think that's the what you had in the other notebook is the last thing we discussed about array insertion.
Okay, but the concept was that the basic concept was that you have you say the key issue is you've got something like this, and you want to, and our default is to add AB like this, right?
Right.
So we want the possibility of adding it in a different way, right? That's the key issue. Mm-hmm. And that's something that applies to lots of operations, right?
Yep.
And what we had imagined was this thing we called insertion, right? Where we say, just like we now have Splice, we would say plus insertion of this, or something like that. Mm-hmm. And that would mean that that is I don't know whether that's the right word, but that is that's being done at a deeper level, right?
Right.
Now, is this a well-defined concept? I mean, I think it is basically a, this can be implemented.
Yeah, I don't think so. And it's not easy to implement, no.
Okay, well,
it's very hard to implement.
Okay, great. Then it adds value. Okay, so, but the main problem we're trying to solve here is the endless use of, hash plus AB, right? Mapping that over the list, right? We're trying to make that simpler. Am I making sense?
And by the way, shouldn't insertion also take like a level spec or something?
Yes, it should take a level spec.
To making that map at some other level.
Exactly. Right. I mean, so the concept would be, thing and some kind of level.
So really though, this is, I mean, it seems like in general, this operation is going to be equivalent to that map.
I would think so.
With a different function, of course.
Right, I would think so. So, I mean, I would not be completely surprised if there wasn't some identity between it and something to do with Splice. Maybe I'm wrong.
No, Splice is, right? Splice
What's
disappeared. That? Splice is
I'm aware of it disappears, but I mean, what is there not? Okay, so one way to think about this insertion thing is that it is, I guess it's just a map. I guess it's just doing the map.
Pretty sure it's just that.
Yes.
Perhaps the question is which operations
Oops,
should be
that's
expected
very irrelevant.
to support this?
Why does this thing not deal with copy? Okay, never mind. Okay, there we go. What's that? Say that again.
Yes, I was wondering which operations are expected to.
Well, let's imagine the case. Let's just imagine if an arbitrary f. So, I mean, this might not work, but let's just think about that for a second. You know, if it was the case that f of, I mean, so this is kind of like some kind of local listability, local threading. Or,
Right.
you know, another possible word for it would be threaded.
But in that sense, it's very similar to the discussion of a splice, in that the splice only reacts to lists. So
Well,
perhaps,
except, but we need to change that. We need a version of Splice, we've talked about this before, that can operate in a given head.
right, but yeah.
Does Splice work with up values, I assume?
Yes.
Okay. Then
But so could Splice work? If you gave Splice a second argument that was a head, could it splice into that head?
I mean, you could certainly write something like that in the top level, but it probably wouldn't be very efficient. So I imagine it's possible.
Okay. So this, imagine, I think threaded is a better name than insertion, by the way.
I agree.
So what would happen? Okay, so this is f list, comma, threaded, blah, 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 AB. Now, threaded would be equivalent to calling thread on, okay, if I say thread f of, you know, AB, right now, that will give this. So what is this thing equivalent to? Threaded, am I being confused? Is this not an equivalent?
Kind of like map thread.
Which is like map
You have
thread?
above with the arist, right. So with the 2x2 array, and the AB is equivalent to map thread of plus, comma, and then those two lists.
This thing here, no, wait a minute. This.
No, the thing you had above, the thing above, that's below %223.
Okay.
Yeah, that's a map thread.
I think we might get ourselves into trouble thinking about this in terms of thread, because the listable threading uses multiple levels of thread.
What do you mean by that?
It's not just a single thread. It basically has to be repeated.
You mean listability repeats?
Right, listability.
Well, let's not give up on the concept of thinking about this as a thread, because map thread doesn't repeat. Right?
But isn't
Correct,
that why
yes.
we want the level? The level would be
Yes.
like subtracting 1 every time until you reach zero.
Well, yes. I mean, we might want an at a level and through certain levels.
Oh, I see.
But
Well,
I mean, go ahead.
would it have through certain levels?
Say it again.
What meaning would it have to do it at multiple levels?
I'm not sure. Because, I mean, Rob was bringing up the idea that listability does things at multiple levels. But I really like the name threaded, by the way. I think that's actually an easy to understand thing. You know, it's a threaded, you're adding it in a threaded way. You know, so, okay, so let's look at this again. What could be, can this work? So what does this exactly mean? This means, okay, so you're saying basically, where did I have that? What is this? What is this equivalent to? If I say, okay, so first of all, if this isn't a list,
Well, right. Well, I mean, the problem is we don't know what that's equivalent to because it depends on list, right? So threaded needs to somehow reach outside, which is why I'm very skeptical of this approach. Right? Threaded needs to know what the other arguments to a function it's inside of in order to know how to.
Well, so does
thread it out.
listability.
No, it doesn't.
So let's try what
Listability works from the top down.
So
And
let's
there's only one
I
rule.
see what you're saying. Okay. Okay, go ahead, Jose.
yeah, let's try what Christopher was suggesting. So that thing you just wrote could be map thread of F and then the list of the various arguments. List 1, A, B, list 2. And then if this happens to be valid, the operation can be done. If not.
Okay, so let me understand what that means, because what I would expect this to do is if this was X, Y, 1, 2,
yeah, and put another length 2 list there.
with another, well, let's just do here. You're saying of depth 2 list here.
Length 2.
Length 2.
Depth, anything you want.
I'm confused now. So, okay, so this.
That's a length 1 thing.
That's the length 1, yes.
Oh, length 2. Okay, UV. Okay, let me understand what this just did. What?
That's like listability. You want to repeat the AB.
I want the AB to go all the way down.
Right. So it needs to be repeated in a list of length 2 to do
Right.
what you're thinking of.
Right.
Right. So, but the whole point is what we're trying to do, and I see Etienne has joined also.
Hi. Yes. Sorry.
What we're trying to do here is understand. So we're talking about your insertion or whatever it's called. We prefer the name threaded right now. And I mean, the overall goal, just to be clear, is this thing here. Okay, so actually Sandra is asking, what would this actually produce? Okay, so this would produce, this would be, let's see, 5. Let's see, what is this going to produce? This would be
5 plus
5.
A plus B, 3 plus A, 4 plus B.
Right. So it is threading down to the lowest level there. And if it was told a level, so this would be, it would be here, threaded down to a certain, thread at a certain level. And this would be, so for example, this would be the level 1 thing, in which case it would be the, this would say threaded at a certain level.
I think that a good way to think about level specifications here is thinking about how you promote the dimension list of the right term. Because in the end, you have
That's what you're saying.
A comma B has to become a 2 by 2 thing, and now it's a 2 thing. So where do you add the extra 2? Do you add it at the beginning of the dimension list or at the end or in between if you have a more complex object? I think that's very...
Right, so what you're saying is, what operation do we have right now that does that kind of replication of a tensor?
I think maybe it was array pad or something like that with a complex syntax. I also implemented in numeric array utilities a symbol. I forgot the name. Maybe array replicate, which is something we decided,
Okay.
few months ago that we should do it just to play with it at least.
That's about constant array.
What's it called?
Constant array.
Right. Constant array is the way to replicate an array.
I see.
Oh yeah, constant array, yeah. And the thing that I did, let me find its name.
Wait a minute. Sander is pointing out that in our live stream that he's already implemented a function called generalized map thread in the function repository. That will be cool. Okay, let's see what it does.
It solves a different problem.
What is it doing?
My recollection of it is that it allows scalars and sort of ragged things.
Well, that's interesting too.
Right, we talked about it.
Okay, so that's a different. That's yet a different thing.
Yes.
Check numerical array utilities backtick array replicate.
Sorry, what was it called? Numerical what?
Numeric array utilities backtick array replicate. You might have to load numeric array utilities. So you might have to do, I don't know, yeah, get. And this is a string or not. Yeah, not. Yeah, you can check information about that, like question mark, and should have a.
What the heck? Oh my God, that was really funky. That was a. How do I? Oh wow, that's exciting. I do backspace and it unpythons it. Well, that's bad. See those spaces there? That's probably a bug in the handling of information handling. Do you know what I'm saying?
Yeah, I don't.
Somebody report that, please.
Yep, I got it.
They're.
And also the way it says symbol at the top is also wrong.
I mean, this is not a top level thing. This is just a.
Oh, I know. I'm well aware of that. I'm well aware of that. This is just a thing where the question mark is not being as smart as it could be. Okay.
And this, I think, is a design we decided quite some time ago. Yeah, you can specify the level that gets replicated and how many times it gets replicated. And
what did we do with this? I mean, go ahead.
Yeah, actually, yeah, the first two lines is the same thing, just explained in a different way. Actually, each line is doubled, just explained in a different way.
Right. Well, so hold on. So this is a function that we believe is independent of all other functions. This array replicate.
We could. Yeah, we could make it a top level. Also, the idea was to, implement it, to play with it, and
well, it should certainly be in the function repository, if nothing else. It should be in the function repository. Now, okay, look, okay. So first point is we need to make forward progress on this threaded idea. And what is the relationship? Oh boy, this is yet a different thing, this level applied thing. Isn't that like array reduce?
Yes, look at the second subsection heading.
Okay, so this, we believe that level applied became array reduce. Is that true?
I think they are.
No. Headdress version versus explicit form. I mean, I'm not convinced that the headdress form is super useful, but yes.
Well, it's like a column-wise addition. How do you do column-wise addition? What's the right way to think about column-wise addition? Is it level applied of plus, comma, or total, comma, 2, or what?
Yeah, I would say total, comma, list 2, probably.
Okay, so this is another thing. So this is another topic here. This is the headdress form of array reduce. Okay, otherwise known as level applied. Okay, Sandra makes a comment here. Okay, hold on. Sandra's saying, adding or subtracting a constant vector from a large set of vectors is something I commonly do. Yes, I agree with you. I agree with you. That's a very common thing to want to do. I mean, this is the most common thing, is you're doing this, and you know, that second thing could be a constant array or whatever, but the main point is you want it to burrow inside and just do that without having to do this, right? We've picked a default, which is, you know, listify at the thread at the top level. Sometimes you want it to listify at the lowest level instead. And that's what we're trying to solve with this. So look, let's, Jose, maybe you can pursue this issue of whether threaded can be made to work, whether this is makes sense. I mean, I think what's going to happen here is, let's say that the lists are of incompatible shapes and sizes and so on. Well, just like listability, it's going to fail, right? And that's okay. You know, incompatible shapes, just like listability would say that. Does that make sense?
Right. What I don't know how to do here is that if we have an array of depth 3, how do you specify whether you want this at level 2 or it's always at
you give a second argument, threaded. So in other words, here, what this would do is it would say, you know, comma 2 or something, would say, do this threading at level 2 in each of these lists. Which means, which is equivalent to that threaded thing, I suspect. Okay, so listen.
Well, I mean, if you have one other list that's well defined, I'm not convinced that's well defined.
Well, it is if they're deep enough. But listen, threaded AB, comma constantly specified level is equivalent to simply constructing that threaded thing is equivalent to constructing an appropriate replicated tensor and then just using listability, if I'm not mistaken.
Or I think it's equivalent to map. I mean, that example we had above, the example I sent it before was kind of a typo written thing, but I mean, it's just mapping at level whatever.
Fair enough. But well,
I'm not sure. I still think map thread, and the number 2 you wrote there could be the third argument of map thread. It's just that we need replication. Yeah.
Yeah, right. Once it's replicated, and maybe there needs to be a way. This is kind of replication based on environment. How much replication depends on how deep the ambient lists are. There's not going to be a way of getting around. I mean, the basic point is there are 2 different defaults that are useful for, you know, adding a vector to a list of vectors, right? And we picked one, and you could pick the other, and we need a way to specify the other. And that's really all this comes down to. Am I making sense? And, you know, we could imagine, as we've discussed in some of these places here, that, you know, in an extreme case, if we think plus is the main thing, you know, we could imagine, I mean, I don't think we have a lot of syntax available to do this. I mean, you know, there is presumably syntax like maybe, no, slash plus doesn't work. That's already taken syntax. I mean, slash minus, but you know, all of these things, it doesn't really make a lot of sense. We'd have to, I mean, I suppose what we could do for code elegance, we could imagine something where we have a, you know, a special character. I don't know what it would be. Let's say a bullet or something that means the threaded version.
It's just a little non-general because, again, you would like to have other levels.
Absolutely. So we need this threaded thing, but this just means the threaded version at the lowest level.
Well, do you mean the lowest level or the lowest matching level?
Oh, interesting question.
Yeah, we have a precedent for that in part setting. So if you set a part, it goes to the first level that tries to go to the first level that matches the dimension of the setting. And that's top down, but we might want to think about this from this bottom up with a matching type thing.
Right. Okay, look, this is something go ahead.
Let me point out that none of this can work without changing the evaluator.
Okay, that's fine.
Well,
Right, because otherwise the list plus is listable, and so then it won't. Nothing will work.
right.
Yeah.
Well, this just has to be a thing that goes ahead of structure, which yes is a part of the evaluator, but we already did that for the packed array stuff. It has to be done before it hits structure.
Yeah, so I think this example here works if f is not listable, or I haven't tested it much, but I think it works if f is not listable. But of course, most of the examples we care about is where f is listable.
Well, okay, so let's say we say, I've got my example here. Okay, so now I say threaded here.
Oh, well, I think this is only a 2-argument thing, so I don't think this is
Okay, fine. Okay.
Right. So
Correct behavior. Is it? Hold on. Yes,
right.
That's the correct behavior.
If you do a /f goes to plus, you'll get
After the fact. Yeah, that's exactly what we want. That's exactly what we want. All right, look, the objective is we got to get to this place. And, we've got at least a somewhat reasonable idea here, so let's study it some more. And let's now come back to the main part of the agenda, which I hijacked here.
Before we leave this, what could be a function that does this from outside? So it takes the array you have in the first argument, then the AB, and it specifies a level at what you want to do. So
kind of the same argument structure as map thread.
Right, something similar. Perhaps you can specify independent levels for individual arrays that what you want to do.
So what are you saying? That this is for what?
So I'm trying to do this.
The explicit version.
The explicit version of this, exactly.
Okay, so this is an implicit
headdress version.
Threading, and now we want headdress.
No. I'm calling what you just did the headdress version.
It's not a headdress. A headdress would be modifying the F.
Oh, okay.
Exactly. Yeah.
Okay. Explicit version.
So going back to Sanders' examples, if we have an array and a vector, and we want to displace the array by the vector, we could have a function that takes the array and the vector.
I see. So what you're saying is, you're saying something like, map within or something.
Mm-hmm. We'll take F,
the original array, and the big array.
Well, is there some way of generalizing it to? I mean, maybe this would make the arguments too complicated, but maybe it would also be possible to generalize it to arbitrary numbers of arrays.
Sure.
Right. Yeah.
Right. So this would be. It's not clear how the argument. Then it would have to be more like map thread, where these two things are in a list.
Right, but I mean, the question is there some way of specifying those that isn't overly complicated and where, I mean, like, for example, you presumably need to specify different levels for each of the different arrays. And there's complicated questions about like the ordering and stuff like that once you have 3. So I'm not sure it can really work without being
right. Well, I mean, okay. One possibility is some kind of crazy syntax with level arrows here.
I'm just saying, even with that, though, there might be ambiguity about the order in which to apply these things.
Yeah, I get it. But I think the obvious thing, if you applied in one of these functions without folding, then it applies simultaneously. It's f of multi-arguments.
I guess my point is that whatever is a problem here will be also a problem in the threaded case, right? Because this is trying to do the same thing. Probably this is even more powerful.
Exactly.
Yes, I agree. But I mean, the threaded case, the default case of low level, you know, it goes to the lowest level and it just adds in the vector and so on. That's the default case that we want. So all other cases are bonus, but important.
Mm-hmm.
And
So
here, go ahead.
The same thing. I mean, this could do the same thing by default. It realizes you have a vector on the third argument and then a matrix, and it tries to push the vector to the deepest level.
Right. Right.
Well, actually, related to that, though, there's the question of how it knows. So if the arguments of f, if f needed to be, let's say the argument order of f was reversed, right? Then you can't just have it so it takes quotes, you know, the big matrix first and then the little vector second.
Absolutely. I see. So how does it know? Right. How does it know that this? Well, okay. How does it know that it should push? What is the semantics of it pushing? Because when you have a threaded thing, you are breaking the symmetry. See what I'm saying?
We can make this to thread through the deepest level of everything.
I see.
I mean, deepest compatible or deepest deepest?
I would say deepest. And if it
What's
doesn't
that?
work, it complain. I would say they have to coincide. Because
But so that means that it would return, it would have f of, it would be list of f of ab comma x comma f of ab comma y, etc. Right?
No, I would say
no.
If ab is a vector, then it will return list of f of ab xy and f of ab 1 2.
I would argue that's deepest compatible, because deepest would be you just apply, you know.
I would have thought it would be this. No, but this isn't right. This isn't right. This way around isn't right. I think this is not a symmetrical thing.
Well, I mean,
what you just wrote, I think, doesn't make sense though, because you're breaking up the AB.
Yeah. Yeah, but then how do you do I mean, I don't understand. What good is this if it doesn't actually do the equivalent of the threaded thing at the lowest level for the plus case, namely this? All right, let's go back to our main part of the discussion, and let's come back to this maybe next week. But I mean, we need to keep pushing on this because, as I say, the one thing we know we absolutely need is this behavior here, right? So generalizing that and understanding how to do that in the best possible way is a fine thing, but that's behavior we know we need. Make sense?
Yes. I do agree with that. It's just that language will probably hide something that we see better with the explicit version, but we will explore.
Well, I understand. Okay, let's come to your actual agenda. Okay, so let me just...
Okay, so this part had two parts. One is some sort of enumeration of various problems that we have discussed at points, but in the first area, the most important thing I wanted to mention was you can close this first point. Let's go to transposition first. So first, we want to implement this. This is not yet implemented, but
really, I thought that was implemented. I thought we had the two-way rule. Wait a minute, the two-way rule thing. What's that?
We plan to implement it, but it's not implemented yet.
Okay.
But we will. I think I'm more convinced now after going through the various things. I'm more convinced that this notation is useful. Now,
wait, there is a version, like there's a usage in the documentation that has the two-way rule thing. Maybe it's different.
It's a one-way rule, right, that we're discussing?
The one-way rule, yes.
Okay, sorry.
Oh, okay. The two-way rule exists. Oh, I see. Okay.
Right.
I thought it existed. Okay. Now, what does the one-way rule mean? Because that I don't understand so well.
Exactly. You can evaluate this code on the left, and we test it. So now, the most important case of this is the case in which we map to the deepest level. So try an array.
Try what would you like me to try?
Try and transpose with an array, any array of depth 3 or something. Try dimensions 2, 3, 4. It's always
Oh, I see. Okay.
clearer when the dimensions are different.
Okay.
Right.
Now, what do you want me to do? You want me to say transpose this?
Right. Now transpose 1 goes to 3, for example. And check the dimensions of that.
So we've cyclically permuted our.
It happens to be cyclic in this case.
Exactly. If you had a 5, if you started with 2, 3, 4, 5, the 5 would be left in its
That's
place.
basically pushing the 2 in the third position in the dimension list.
Yeah, inserting. I think that would be the best way to describe it.
Right. So if I go here,
It's not really inserting because it's removing also a 2, so it's moving the 2.
It's yeah. We're moving it, and it's
one
yeah.
to
Okay, fine.
3. Hold on a second. 1 to 3 means yes. Okay. So it's taking what was level 1 and it is making it level 3.
Yeah.
Right.
Yeah, that
And-
seems
and-
useful. Because
is
basically, you go ahead.
Is it cyclically permuting everything in between?
Exactly.
So if you had like a 2 goes, well, I guess we'd need one more level. So add a 6 and you do like a 2 goes to 4.
It looks like it's equivalent to calling delete and then calling insert, which is probably the right thing.
Yeah.
That right? Hold on. So 2 goes to 4.
Right. So levels 1 and 5 were unchanged, and then 2, 3, and 4 were sort of cyclically permuted.
Right.
I
Because
mean, 3, 4, levels 2, 3, and 4, which are 3, 4, 5, became 4, 5, 3.
That's why the rule is needed, because this is not equivalent to 4 goes to 2, while the two-way rule is symmetric in that sense. It's just an exchange.
Yeah,
So
this-
when would we use this?
I found this very useful when I developed a reduce, for example. I would use it everywhere. Yeah.
Yes. Indeed.
Even to describe. So there was a notebook a long time ago. I think it's called array operation -- array reduce, etc. And it was for me to understand array reduce and level apply and even map thread and map. And by using this transpose, it was very easy to code everything, and everything was clear.
So basically, the basic point of this kind of transposition is meet me on a certain level in some sense. You've got an operation, it has to correspond. Some level has to correspond. Is that right? I mean, is that the way to think about this?
Yes, I think so. And for example, one case which is extremely useful, and we use it a lot internally, is when you are sending the first level to the deepest level, or vice versa.
Does that go, say, 2 arrow -1, or does that not supported?
Well, I have a question further down saying whether we want to support that. It's a bit weird to have a -1 inside transpose. So perhaps we need a different notation. But that particular case, I have internal functions called array of lists and list of arrays. Imagine that you have a 3 matrix of coordinates x, y, z. Sometimes you want a list of 3 with the array of all x's, the array of all y's, and the arrays of all z's.
Wait a minute, why isn't that transpose?
It is a transpose, but it's a transpose that people have to work on the permutation for some time.
Okay, but
that's sort of what the flatten does to some extent too, with that alternate argument for flatten.
Correct, because flatten incorporates transpose.
Right.
Yeah.
So wait a minute, are you proposing some kind of new functions that are special cases of this?
Well, I'm asking whether -1 is acceptable. I mean, it doesn't look too weird to have 1 goes to -1 and -1 goes to 1.
I don't think so.
Transpose.
No, that'd be great, because I have functions I've had to write called transpose first to last and transpose last to first, because it's so hard to figure out the permutation.
Exactly. Exactly.
By the way, Rob, you have a very strange background noise.
Oh, sorry, that was my chair creaking. Oh,
Oh, no, but no matter. But do we think that there's a useful named function that represents some of these kinds of things? I mean, Rob said he had one that yeah, okay. Well, all right. So, I mean, to me, it seems, anybody objecting to this arrow notation, this rule notation? Seems good to me.
gosh, no, I think it's good.
Okay.
Yeah.
And I think the -1 is fine too.
Okay, good. So
I do have one question though. What happens if you want to do multiple? If you want to, I mean, is it well defined to do? No, I think you just have to do multiple transpose operations. I'm just saying, if you want these levels, like for example, let's say you want some kind of block matrix that is where you say levels. Okay, so imagine you needed
I
something
mean, you could do one after the other, but then it's probably just much more clear if you just write multiple transposes.
Well, no, it's actually, I think you could do one after the other, and I think you could actually implement it by figuring out the permutation for each one, and then permuting the permutation according to the dimensions.
What about something like this? Does that make any sense?
Ooh.
Well,
I'm not even sure how to try to understand that.
Well, so what I'm imagining is, let's imagine you have a block matrix. Okay, so you've got, maybe I'm confused, you've got a matrix of matrices, okay? And you want to take the, let's say more to the point, you might have levels 3, 4 goes to levels 1, 2. I suppose that's does that make any sense?
well, it would be a matter of finding the corresponding permutation. Now, the general case of this might be complicated because this is not just a product of two permutations that might not commute.
I understand, but is this well defined what this should mean?
Well, in this case, which is simple, I think yes. But if you have an array of level of depth 7 and there is nothing consecutive, you don't know what to do with intermediate levels.
So in other words, if you say if these two levels are disjoint.
Mm-hmm. If this was 1, 3 goes to 3, 7, I have no idea what to do with levels 2 and 4, etc. It's not so simple as just cyclic as before.
Yeah, I think it might be better as a sequence of one-way rules, and then you can always figure out the permutation.
Yeah,
Right.
but maybe that's not conceptually how you want to think about it.
Yeah, I see what you're thinking about. I'm not clear as to whether it's always well defined.
Mm-hmm. But more than well defined, it's a matter of finding an arbitrary choice of what to do with the other levels.
Yeah. Sandra is also commenting, what if the second thing is degenerate? That's totally weird. Well, okay, I think this is not making it this. I mean, and you can always fold in, if you really want to do multiple of these transposes, I guess you can always fold them in, or we can provide a syntax where you can have a list of these rules.
Yeah, it could have a flattened thing like 1 and 3 goes to 7. It's flattened and then put at 7. I don't know if.
Well, right. I don't know if that's a good idea either.
Yeah, I think it might be better to keep that behavior in flatten, honestly.
Yeah.
Because at least if you think of them as permutations, you can certainly handle a list of rules easily. If you don't, if they're no longer permutations, then it's really problematic.
Right.
Okay. Nick is asking about what if you move a level to level 0? Could it do something with the head?
No,
that's not an idea.
Totally weird. it will become a multi-headed creature because you might move a level that has many elements in it to the head. Ooh, that's really wild. Okay, so this seems like a good thing. All right.
Perfect.
Contraction.
Yes. So in contraction, we have various functions that do contractions. So first, the general idea of contraction is having repeated indices inside a table. And then we have this G applied from outside, which is usually plus or list. But trace can do all these things, right? So the only limitation in trace, which I find annoying, is that it always traces the top levels. It cannot trace intermediate levels.
I understand. It's tracing some number of levels down, but if you have a tensor where you want to contract over, what is the relationship between array reduce and contract?
Do you have an example for that?
And what's tensor contract? How does it relate to this?
Tensor contract can do the contractions and multiples in any order, but it's always with plus. Tensor contract is the linear algebra version of this, so always plus. It cannot do any other G. And
why can't it be generalized?
Well, we don't want it to be generalized, right? It's a math operation.
Right. It's a bit like saying we are going to generalize debt to do other things. Doesn't feel correct.
Generalize what?
Debt.
Oh, yeah. Okay. So
that's why there is a separate array contract that I placed in the Wolfram function repo to do this.
Okay.
But if simply trace this argument that is currently an integer could be a list of levels, I think it would be great.
So wait a minute. If that argument 2, which right now means 1, 2, could be an arbitrary list of levels, then you would have the same operation.
Exactly.
Although arguably, it's kind of more like a map or apply operation that should have its function first.
Well, it's an afterthought in a sense. It's like we do this in many places like inner or distribute, etc., in which we put the functions at the end.
Well, the default function is what? Is plus?
It's plus.
Okay. So you're saying we don't need array contract if we generalize TR to have.
Right. There is one single detail, which is this a detail that will appear multiple times, and it appears in array reduce. That's something I wanted to raise, which is that when you have these various operations acting on some levels, but not all of them, there is always the question of what to do with the other levels. And there is always the two main choices. We put them at the beginning or we put them at the end. And various functions do different things. It's also very similar to the choice of threading at which level. Threading.
Right.
Threading from the end.
Okay, hold on.
That's. I think you should try to open this notebook, array operation -- array reduce, because that's. I was kind of summarizing the idea we had in a previous meeting, and the difference between array reduce and level apply. Like you were really into level apply, and I actually argue it's less useful. It's more intuitive to do the map column, and that's exactly what Jose just said. So array reduce is actually putting all the other levels at the end, I think. No, at the
beginning.
At the beginning, exactly.
Exactly. Put things at the beginning.
And level apply put all the other level at the end.
Right.
Is it equivalent to array reduce otherwise?
I think the best way to understand array reduce is to compare it to flatten. And there is a subsection further down comparing both. I think that's the easier way. A comment. This section on a comment. So let's take this array. Evaluate that array.
Which one?
The next one. This one. So we take that array, which is an array of depth 4 with levels 2 with dimensions 2, 3, 4, 5.
Mm-hmm.
Now, if you do this flattened array of 2, 3, we are flattening levels 2 and 3 together. So dimensions 3 and 4 now become a dimension 12. But you see what we do with the other 2 levels, the 2 and 5. We put them at the end.
Yes.
Okay, so what Etienne is saying is that array reduce in the same scenario puts the 2 and 5 at the beginning, which is the situation further
Yep.
down. And so this choice of what do we do with the other levels appears in many of these operations when you can act on arbitrary levels. And an array contract has that very same problem too.
How should I think about this? I mean, okay, let's talk physics and tensors and things. Is there any analog of this there? I mean, usually in tensors, you're doing operations in situ with, you might, do a summation convention over indices 3 and 6 or something. But then all the other indices stay in place, don't they? Where does the result from 3 and 6 being Einstein's sum, so to speak, go?
Well, that's turned into a scalar. In those cases, those levels disappear.
Oh.
Right. The point of tensor contract is that it necessarily reduces the rank by 2, whereas flatten has this ability to not. I mean, it can make levels disappear, but it can make them disappear sort of, right, not in a, it's not an all or nothing sum, right?
Okay, how should I think about this? Where do you put the remaining levels, either in terms of linear algebra or in terms of anything else? Or in terms of depth first search or whatever? How should I think about this?
So flatten, as Itai was saying, flatten, the thing with flatten is that it takes several levels and produces a new level rather than 0 levels. So now the question is where to put the other ones with respect to this one. In our case,
it produces one new level.
One new level. The one
so
with
array reduce produces how many new levels? Array reduce takes n levels in and produces how many levels out?
That depends on the function you put in the first argument. That's
in general, for like a function like total, it will go from n level to n minus the number of levels specified in array reduce.
Okay. But so then there's a block of levels that were produced by the function in array reduce. Where do they get put? Do they get put in situ relative to the other levels, or do they get put beginning or end?
At the end. So
at the end.
The level that you perform operation on always have to be at the end in all of these functions, I believe. So if you check the notebook on the right, you see even map. What is map really? So if you go down, you see map. Map at level 3. What it does is that the first 3 levels are untouched.
Yeah, right.
And then everything else is processed. And so in the general case, you have only 3 levels left. I mean, you could have more if your function f is not producing a scalar. Map thread, what it does is that it takes...
right, you're making an assumption there that... Oh, sorry, you're doing it precisely at level 3. Right?
Exactly, at level 3 in that case. Map thread, what it does, if you say map thread level 2, it takes the first level always, move it at, of like two further, and then apply everything that starts from this level to produce something. But always applying at the end. Level apply that you proposed some time ago, because it's intuitive map colon. That's really, I think, its main quality. The rest, not so much. Level apply level 2, you take level 2, what is that? You put it at the top and you apply f on everything else. That's why it's not that useful, is that you specify, I mean, it's a bit like map where you specify what to keep and not what to apply on. And typically, and then array reduce where it moves the level at the end and apply on this level.
Something I think it's important here is to realize that array reduce is a combination of 2 operations. The first one is always a flatten or transpose, and the second one is a map, and they are independent.
Sorry, say that again, Jose.
Yes, so that's the way I understand now array reduce, which is the combination of two operations consecutively. First, always either transpose or flatten, and the second is a map.
I see.
Right. And the kind of funny thing is that the actual reduction part in the name is a property of the function, right? Because if you have
Right, if the function returned something of the same shape as what went in, it wouldn't reduce at all.
Like identity wouldn't do. Yeah.
That's not completely stupid that array reducive identity doesn't do anything.
Well, it's a flatten.
Maybe it shouldn't be called reduce then, if it's not guaranteed to reduce.
No, I don't agree. Array reducive identity, the fact that that does nothing seems just fine to me.
Well, yeah, but there are other functions which are not identity.
I mean,
for which
in principle, I think in practice, basically never happened.
Yeah. We should, by the way, give that example of array reducive identity in the properties and relations section.
Yes, I've added plenty of examples there, but it's not true that array reducive identity does nothing. It is equivalent to flatten. It can still flatten or transpose.
I see.
Because it's a combination of both.
Okay, so what are we?
So I just wanted to raise this general topic of what to do with the other levels.
Yeah. And what is there any intuitive way to understand? You know, one is moving. I'm still very confused. I mean, you're basically saying, do the operations at the top, and then some of the elements in those operations will have trailing pieces that are lower. Otherwise, if you're doing the operations and you don't know what's coming out, there's no way that can be anything other than at the bottom, can it?
Exactly. It has to be the level at the bottom that you perform operation on, always.
Not really. Think of what trace does. So trace is doing the operations at the top and leaving anything behind inside. Right.
That means that it's leaving as lumps, you know, as a single lump of stuff, the trailing sub-tensor.
Right.
Right.
Exactly. It doesn't care that. So for example, when you have an array of depth 4, you could treat that as a matrix of matrices and perform matrix operations on the first two levels.
Yeah,
not
right.
Caring about the fact that the elements are matrices themselves.
Oh, and why can't you do that at any level? Why can't you go, you know, why can't you have a list of matrices of matrices and then do that operation on levels 2 through 2 and 3?
Exactly. You can. Perfectly, you can. Yeah.
Okay. Where basically what we're saying is treat things below this. It's like outer has this rather crazy, you know, number that it gives as its, you know, last argument that says treat it as atomic below this level.
Exactly. Yes. So for example, here in array reduce, in which we perform operations on 2, 3, it could have decided to leave 1 at the beginning and 4 at the end. That's another possibility.
Treat as atomic trailing levels.
Right.
That's the main issue. How many trailing levels do you treat as atomic? Or do you treat as atomic trailing levels, or put your result at the end of the level list?
Mm-hmm. So this is what we do with this integer at the end of outer. In outer, we say everything beyond level 3 is atomic.
Right.
And so everything is left inside beyond that.
So these other operations, like array reduce, maybe I'm confused, but is there a sense in which there is also a question of what gets left atomic at the end? So in other words, this is the there's a notion here of kind of you know, okay, so there's the application levels, the atomic levels, And and so application levels means what you operate on, and the atomic levels means the trailing thing you leave.
Mhm.
And then what else is there? Then there's also the application levels. Okay, application levels is what you take in.
Right. So those would be the third argument in array reduce, or the second argument in flatten, etc.
Okay, the atomic levels, what you leave as lumps.
Mhm.
What you leave as innermost lumps.
Right.
Okay, so e.g. outer has such an atomic levels idea. What else has an atomic levels idea? You're saying trace does or not?
No, the array contract function above does, but as far as I know, in the Wolfram language, in system functions, only outer right now.
Okay.
But the point is that this question appears, and what we do in all cases is just to have a default. Flatten puts everything at the bottom.
Right. So this is a notion of. I mean, I don't think this term atomic levels is absolutely terrible, but maybe there's a or what's a better term for it?
Groupie levels?
What's that?
Groupie levels?
Say that again.
Groupie. That's in like groupies, people who are just sort of hanging around.
I know what groupies. I mean, I haven't heard that word used in a long time. I think it's gone out of fashion, but it's along with groovy, groupie, and groovy groupies, perhaps. Okay. In any case, why is that relevant?
Right, because they're just right. They're not involved in the action.
Right? That's a stretch. I mean, I think, but rather what I'm thinking of them as their irreducible lump.
I personally call them effective depths or effective ranks.
Well, I mean, that sort of, but I thought we were talking about the levels we're not touching, right? Which aren't necessarily linearly ordered in the, right? The effective depth is, the depth of the levels we're actually manipulating. Whereas I thought we were trying to name all the levels that we're not manipulating.
Well, the point is that when you have levels, you have application levels up to 4, then up to 4 you have to handle them. And then the question is what to do next.
What is all this stuff?
So this is this is an idea that there is an ainsum function, and this is just a trivial way of implementing what they do here. And it's another way of doing summations, traces, sums, etc. I wanted to show.
This is, I think, a longer discussion.
Yes, we spend much time on the other one, but this is simpler. This way of handling.
I mean, is it literally the Einstein summation convention?
It's a generalization. If you open comments, so these ainsum functions generalizes 2 ways.
I see. They can repeat more than once, more than twice.
Exactly, which we can do with trace, but trace will insist they have to be the top ones. That's why I want to generalize to any. And then the other thing, which trace already does too, is that it can take functions other than plus.
Sure.
And their ainsum function only takes 2 possibilities. It's either list or plus.
Okay, fine, or whatever.
But the nice thing is that they can do that with indices.
You mean say which index is to be reduced in this way?
Right. So the standard way of doing contractions, etc., in linear algebra is just to repeat indices. Now there is this notation of having indices go to another list of indices, and the convention is if the index appears on the left, on the right of the rule, then you are using list. If it doesn't appear, you are using plus.
well, whatever. I mean, okay. Look, we let these meetings about list operations kind of go to seed here a bit over the last few months. I think we need to,
So we have identified a few things that are already implementable, or at least.
Yes, I think so.
Yes.
Ethan comments that this conversation was poorly motivated, and the question is, what do neural net developers find annoying? So we have some neural net developers here, so maybe you can comment on that.
Jérôme, Matteo. I mean, for sure, this manipulation of array is super. That's actually what motivated it.
I'm aware. So
yeah.
The question is, what is the specific thing that you need that we don't yet have?
Oh, broadcasting.
Right, which is what we talked about, which is what we're calling threaded, and what we talked about at the beginning here.
Yes, and yeah, I mean, we already have this in the framework, but it's to be able to express it.
I know. That's the primary thing. That was the number one thing that I was trying to get us to focus on, was how to do that. Right? And I think we have a concept now, and we just need to work it through. Okay, is there anything else you want to bring up there?
I think, yeah, I mean, these reduce, that's typical operation that I've done in neural network.
Okay, all right, okay.
The transpose, I think, will be useful as well with arrow. I think, I don't know, Jérôme, Matteo,
right.
If there's something else.
No.
Okay, Nick is commenting that he had an auto-contractible array object once where negative dimensions correspond to contravariant indices. Isn't that how things like, how does exact do contravariant indices, Jose?
Yes, also with a minus in front. I mean, a plus or no sign is covariant, minus is, sorry, the other way. Plus is contravariant, minus is covariant.
But the notion of covariance versus contravariance is a creature of tensor analysis that doesn't seem to be, I mean, doesn't have a more general role, does it? I mean, the fact that you're, introducing metric tensors to raise and lower things seems like a detail of operating, with tensor analysis on manifolds and things that does not have a generalization. Is that a true statement?
It's linear algebra. In linear algebra, you have functions and cofunctions, or vectors and covectors, and you need the separation. It's like positive and negative. It's just two possibilities. But the general calculus of indices allows for more possibilities beyond linear algebra.
Wait a minute. Just explain mathematically for a second why. What is it about quotes linear? You're emphasizing the word linear.
Yes.
Why does that lead to just these two cases?
Because the origin of this is having linear operators and then having their dual. So there is a duality. There's a fundamental duality in linear algebra that leads to covariant and contravariant. And that's not the case in general index computations.
Explain, just for my mathematical moment here, explain the way to understand that duality.
Well, I mean, contravariant indices are indices in the dual space, right?
I'm aware.
Space of linear functionals.
Right.
And right, if you just have random arrays of numbers, but you don't have an operator space structure, then there's there's no such thing as a contravariant index.
Yeah, actually, it's kind of cool in our hypergraph thing that's kind of below indices. What this will correspond to is nodes versus edges. Okay.
Yeah, it's one of these dualities with order 2. The dual of the dual is the original thing. So that's the whole.
Right, that's quite interesting. I hadn't really internalized that before. That's exactly how, because in our setup, these spatial coordinates are effectively, determined by positions of nodes, and then there are these, little pieces of geodesics that represent the tangent space. And anyway, okay, so that's how this works. And by the way, I mean the for what it's worth, and we should wrap this meeting, but you know, one of the big realizations of recent times has been that these hypergraphs are essentially below tensors. They are, if you make a bunch of equivalence classes of GD6, you kind of assemble or actually of nodes, you assemble a tensor index. But the things you have for individual ones are sort of below the level of an actual tensor index, for what it's worth. Probably more understanding of that can be had in due course, but
right. Let me just also observe that in the complex case, right, you actually have 3 other spaces, because you also have the conjugated vector space and the dual conjugated vector space, which is how you end up with dotted and undotted indices.
I haven't done enough complex tensor stuff. Okay. All right, I think we're supposed to wrap this meeting. I believe we have another meeting which will involve some of the same people coming up in just a couple of minutes here. Okay, I will see you guys. Actually, Nick is saying, think of covariant indices as output and contravariant as the input for process. Yeah, well, or the other way around. Sounds good. Okay, see you, some of you.